Hey everyone, welcome back to the Trending Tech Show. I'm Alex, and today we're cracking open the secret sauce powering smart search, modern recommendations, and yes, even the memory of chatbots like ChatGPT. If you've heard the buzz about vector databases but aren't quite sure what makes them special, this episode is for you. Joining us is Sam, an expert in applied AI systems and vector search. Sam, welcome to the show.
Thanks, Alex. I'm excited to help peel back the layers on vector databases. They're a hot topic for good reason, and I think anyone interested in AI, data, or how modern apps get so smart will find this really interesting.
You just set the table perfectly. So, let's start simple. What exactly is a vector database, and why are people suddenly talking about them everywhere?
Great opening. At their core, vector databases are specialized systems designed to store, manage, and search collections of vectors. A vector, in this world, is really just an array of numbers that represents some data, like text, images, or audio, captured in a way that lets a computer measure similarity. Instead of searching for exact matches, you ask, what's most similar to this? That's a huge superpower for use cases like recommendations, semantic search, deduplication, and more.
Similarity search is a key phrase there. Could you walk us through an example, maybe with text or images, of how this works in practice?
Definitely. Imagine you type healthy pasta recipes into a search engine that uses vector search. Instead of looking for just the words healthy, pasta, and recipes, it sends your query through an AI model that turns it into a vector, basically a summary of what your question means. All the recipes in its database have been embedded the same way. Now, the database finds which recipes are closest in meaning, not just in keywords, by comparing vectors using mathematical measures like cosine similarity. So you'll see relevant vegan pastas, even if vegan isn't in your original question.
So, it's like teaching the computer to understand the meaning behind the words, not just the words themselves. You use the word embedding. What exactly is an embedding in this context?
Embeddings are the bridge here. They're dense sets of numbers created by machine learning models, designed so that things with similar meaning get mapped to points that are close together in this high-dimensional space. Think of a big room where every book or photo or document has its own unique spot. If two things are similar, they end up as next-door neighbors in this room, even if their original words or pixels are very different.
That's a great analogy. Now, we keep hearing about tools like FAISS and Pinecone in the vector database conversation. Can you break down what each does and how they differ?
Sure. FAISS, which stands for Facebook AI Similarity Search, is an open-source library engineers use to build their own high-performance similarity search systems. It's like a sophisticated toolkit, very flexible and fast, especially if you want to tweak things yourself or use your own hardware, like CPUs or GPUs. Pinecone, on the other hand, is a fully managed vector database service in the cloud. It hides the complexity and handles scaling, real-time updates, and even advanced metadata filtering for you. If FAISS is for building your own race car, Pinecone is like calling a rideshare service. You just need to get going without worrying about what's under the hood.
FAISS gives you raw power and flexibility. Pinecone gives you convenience and scale. I'm curious though, what's actually happening behind the scenes to make searching these high-dimensional vectors fast? Surely you can't just check every single vector one by one, right?
Searching every vector would be painfully slow once you get beyond a few thousand or millions of records. This is where clever indexing comes in. FAISS, for example, supports methods like HNSW, which is a graph-based algorithm letting you jump quickly to neighborhoods with similar vectors, and IVF, which clusters vectors so you only need to search a few cells. There's also PQ, or product quantization, which compresses vectors to save memory but keep search fast. These techniques mean you can find the most relevant matches in milliseconds, critical for user-facing apps.
And is Pinecone using those same indexing tricks under the hood?
Exactly. Pinecone uses optimized versions of HNSW and IVF with PQ as well, but packages it all up so developers don't have to tinker with index parameters or worry about infrastructure. It automatically manages scaling, so you can go from 1,000 to 1 billion vectors without changing your code.
Let's tie this into real-world examples. How are FAISS and Pinecone being used in practice? Maybe in ways people wouldn't expect.
For FAISS, academia loves it for semantic search in research databases, say, surfacing relevant papers out of millions using embeddings. E-commerce platforms run recommendations by finding similar products based on user behavior. Social media giants use FAISS to spot near-duplicate or offensive images quickly. And even in bioinformatics, FAISS helps researchers compare DNA sequences. Pinecone, thanks to its managed approach, is popular in production apps needing real-time updates. Music streaming services use it to instantly personalize song recommendations. Retail apps combine visual and text search to show you similar clothes across catalogs. And customer support chatbots use Pinecone to instantly fetch the most relevant help article, even as new ones are uploaded every minute.
It sounds like if you've ever received a just-for-you recommendation or asked a chatbot a complex question, you've probably touched a vector database whether you knew it or not. When would a company choose one option over the other?
If you need tight control, like custom deployments, maybe for strict data privacy, or you want to run on specific hardware, FAISS is a great choice, especially for research or batch jobs. If you're building dynamic, user-facing apps where data changes constantly, and you don't want to maintain infrastructure, Pinecone or other managed services are ideal. It's all about balance, flexibility, and tuning, versus speed to market and scalability.
Now, implementing these systems isn't just plug and play, especially at scale. What are some best practices teams should be aware of when building with vector databases?
Good question. Some key tips. Always standardize your embedding dimensions to avoid technical headaches, like using a consistent 768 or 1536 dimensions, depending on your model. Attach helpful metadata, such as timestamps or labels, so you can blend semantic and structured search. Normalize your vectors, especially when using cosine similarity, to be sure distance calculations are meaningful. Choose your index strategy wisely. HNSW is fast for recall, IVF is better for very large static datasets, and PQ lets you save memory if you're at huge scale. And whatever tech stack you pick, benchmark your search quality and speed early. Start with a proof of concept using a small chunk of data rather than everything at once.
Get your feet wet before you dive in. What about scaling up and handling huge, fast-changing datasets? Any challenges teams should watch for?
There are several. First, indexing high-dimensional data is resource-intensive. Doing it in batches can bring a system to its knees if you're not careful. Keeping the whole index in RAM is quick, but gets expensive. Hybrid storage strategies, splitting between RAM and SSDs, help balance cost and speed. For dynamic updates, say user edits or new uploads, some systems struggle to keep everything fresh in real time. Pinecone's real-time upserts help here, but if you're self-hosting, you'll need to architect your indexing for rolling or asynchronous updates. Don't forget embedding drift. If you change your embedding model, you have to reprocess and reindex everything. Finally, operational excellence is critical. You'll want to tightly monitor query latency, resource usage, and recall accuracy, and have solid backups just in case.
Sounds like running vector databases at scale is a real test of both technology and teamwork. Are there emerging trends or new technologies in this space that excite you?
Lots, actually. In 2023, we've seen hybrid search take center stage, combining vector and keyword matches for smarter, context-aware queries. Open-source tools are exploding. Chroma, Qdrant, Milvus, and even Postgres extensions like pgvector let you bring vector search to traditional SQL environments. Models are evolving too. New open-source embeddings and multimodal models let you search across text, images, even audio. Hardware's getting specialized. Dedicated chips, GPU acceleration, and even neural databases are pushing the performance boundary. Plus, monitoring and observability tools are cropping up to help teams track pipeline health and search quality.
And for companies looking to deploy at scale, what solutions are emerging to tackle these notorious challenges, like resource limits and operational complexity?
Managed services, like Pinecone or Zilla's Cloud, offload a ton of the infrastructure management. There's also a movement towards tiered storage, using RAM for hot data and disk for colder archives, so costs don't spiral. Some vector databases offer native support for hybrid search, batching, and real-time updates. Embedding lifecycle management, keeping track of which model created which vector, is becoming more automated, so you can re-index safely when needed. Most critically, a growing ecosystem of benchmarking and monitoring tools is making it much easier to spot, diagnose, and tune performance bottlenecks before they hurt users.
Those are excellent points. One last question. For developers or business leaders starting out with vector databases, what's your biggest piece of advice?
Start small and validate early. Don't try to index your entire data lake from day one. Grab 10% of your data, measure your recall and latency, tune your indexes, and experiment with hybrid search and filtering. Once you're happy with the results, then scale up. Also, think carefully about your embedding model and how you'll manage changes over time. Embedding drift is real. And finally, consider managed options unless you have a good reason to do everything yourself. It'll free you to focus on building features, not babysitting your infrastructure.
Wise words. Measure, test, and grow smartly. To echo it all, vector databases aren't just hype. They're the brains behind smarter search, recommendations, and even AI assistance. Whether you're a developer, architect, or business lead, understanding these systems' basics and their challenges opens doors to the next wave of intelligent applications. Sam, thanks so much for joining us and making a complex topic so accessible.
Thanks, Alex. It's been great chatting, and I hope everyone leaves a little more vectorized in their thinking.
Thanks again to Sam and to our audience. If you want more tech deep dives, be sure to subscribe. Remember, the future of search and AI isn't about matching words, but matching meaning. Until next time, keep exploring.